first of all, what are kinematic equations for linear motion? So we know kinematic equations for uniformly accelerated linear motion are v is equal to u plus at, s is equal to ut plus half of at square, then v square is equal to u square plus 2as, right? And similar kinematic equations for uniformly accelerated, if you have uniform angular acceleration, then for rotational motion we have final angular velocity omega t is equal to omega naught plus alpha t. It is analogous to v is equal to u plus at, right? So this is final angular velocity, this is initial angular velocity, alpha is angular acceleration and t is time. Okay, theta is analogous to the displacement, right? Theta is the angular displacement, it's equal to omega naught t analogous to ut plus half of alpha times t square, right? So just replace a with alpha, okay, initial linear velocity with initial angular velocity and linear displacement by angular displacement, so we get this equation. And then there is omega t square, final angular velocity square, is equal to omega naught square plus 2 times of alpha theta, right? So these are the three equations, we know them, right? So we have studied them in circular motion. Okay, so three kinematic equations. Now after that, so we had touched upon the angular momentum, right? So we saw the angular momentum of one particle earlier. So let's talk about the angular momentum of a rigid body. So first of all, what is angular momentum? So suppose you have some particle, okay, this is particle of this body, let's say, okay, its mass is m is the mass of the particle, right? So then its linear momentum p bar is given by what? P bar is given by m times v bar, okay, mass into velocity, right? So m is its mass, r bar is suppose its position vector with respect to some origin, okay. So look at this apple, r bar is the position vector of this small particle, okay, small particle of the apple with respect to this origin, okay. And suppose when this apple rotates about this axis, then this mass, it will move with some velocity at this point, right? So its velocity is suppose v bar, then we can say angular momentum of mass m at any given time, L bar is equal to what? R bar cross p bar, okay. Angular momentum is defined as the cross product or vector product of position vector with linear momentum, right? So we had defined this earlier also. Angular momentum is defined as cross product of r bar and p bar, okay. So then see, r bar can be written as, okay, p bar is equal to what? M times v bar. So we can write the angular momentum as m into r bar cross v bar, right? Because p bar is m times v bar. And then r bar can be written as sum of one vector along the axis of rotation and one vector perpendicular to axis of rotation, right? So this r bar can be written as r parallel bar plus r perpendicular bar, okay. If you see that this is r bar, it can this is r bar, it can be written as addition of this one and this one, that is r parallel and r perpendicular, okay. So we have broken down r bar into those two vectors, right? So therefore your angular momentum is, which is m times r bar cross v bar, it is m times r parallel plus r perpendicular, okay, cross v bar, right? Now what is r parallel? It is parallel component of r bar, okay, parallel to what? Parallel to the axis of rotation. And r perpendicular is component of r bar perpendicular to axis of rotation, okay. So now see, we are going in little bit deep, but you will understand that, okay. So see, L bar is the angular momentum. Now we can just multiply this bracket with this v bar, so we get two terms. So m multiplied by r parallel bar cross v bar plus r perpendicular bar cross v bar, okay. And then you can multiply with m, so you get these two terms, m times r parallel bar cross v bar plus m times r perpendicular bar cross v bar. So out of these two terms, now one term is the radial component of angular momentum and one is the axial component of angular momentum. Okay, so this is total angular momentum. This term is the radial component of angular momentum and this term is axial component of angular momentum. Okay, right. So we'll say that this term is radial one and this one is axial one. So we are not just saying it for the sake of saying. Okay, we can find out the direction, right? So what is R parallel cross V bar? So see here in this diagram, so look at this particle, it's rotating, it's revolving in circular motion, let's say, because apple is moving, apple is rotating, so each particle of apple, it will perform circular motion, right, about this axis. So this is your particle of mass m. So when the apple rotates, this particle, it's performing circular motion. So at this point, its velocity is directed along the tangent, right? At this point, its velocity is directed along the tangent. So then this was our origin. So from this point, we had drawn this vector. This is r parallel bar and this one was r perpendicular bar. Okay, this one is r perpendicular bar. And then what do you want? So you want to find out what is r parallel cross v bar, what's that direction? So see, if we say that this is x direction, this is y direction, this is z direction, then r parallel, okay, the axial direction is y direction, right? So r parallel bar can be written as r parallel into j cap, okay, the unit vector in this direction. Okay, similarly v bar can be written as v bar is in this direction. Okay, then this is along negative z axis right now. Okay, it's along negative z axis, so I can say minus k cap, right? So j cap cross minus k cap, what does this give? J cross k gives I, right? You want j cross minus k, so it will give minus I cap. So it is along negative x axis, right? It's along negative x axis. What does that mean? It is directed towards the center. So this is along the radius and towards the center. So this is radial component of angular momentum. Is this thing clear, everyone? Yes, no? Okay, good. So this is the radial component of angular momentum. Then you can find out r perpendicular cross v bar. Okay, what's the direction of this one? So see, r perpendicular is directed, it's directed along what? Positive x axis. So I can say that this is m multiplied by r perpendicular multiplied by I cap. Okay, then you have cross v bar is directed along what? Negative z axis at the moment. Okay, so v bar is v multiplied by minus k cap. And then what is I cap cross minus k cap? It's j cap. Okay, right. So this is m r perpendicular multiplied by v multiplied by j cap. Okay, so what's its direction? It's along the axis. So this is axial component of angular momentum. Okay, is this thing clear? Are the two components clear, everyone? So this is radial component of angular momentum, L radial, let's say, and this one is axial component, L axis, right? Axial. Okay, is there any doubt in this? To anyone? No doubt, right? All right. So you have two components of angular momentum, right? Now, what will be total angular momentum of body? So see, we talked about angular momentum of one particle only. If you add up angular momentum of all particles within the body, you will get total angular momentum of the body, right? So what is total angular momentum? It is angular momentum of first particle plus angular momentum of second particle, so on and so forth, up to plus angular momentum of nth particle. Okay, so you can just write it as summation of Li bar. Okay, summation of Li bar, angular momentum of all particles. Then now this is an important point, that for symmetric bodies, and we are going to talk about symmetric bodies only most of the times in this chapter. So for the symmetric bodies, the total radial component of angular momentum is 0. Okay, total radial component of angular momentum would be 0 for symmetric bodies. Why is it so? So for an example, suppose you have this particle. So if this is a symmetric apple or symmetric body, any symmetric body, so then for every particle on this side having mass, let's say m, you will have particle on the opposite side having the same mass, right? Angular momentum of this one would be directed like this, angular momentum of this one would be directed like this. So if you add it up, what do you get? You will get 0. Okay, what did I say? Angular momentum, not angular momentum. Radial component of angular momentum of this particle is directed like this, of this particle it will be directed like this. If you add it up, the total will be equal to 0. This thing is clear. For symmetric bodies, radial component of angular momentum is equal to 0. Right? Okay, clear to everyone? Okay. So then, suppose a body is symmetric about the axis of rotation, then the angular momentum of body is directed just along the axis of rotation, and that means we just need to take the axial component of angular momentum and add it up to get the total angular momentum of the body. So what is axial component? It is m into, see, for one particle it is m multiplied by r perpendicular into v. Okay, so m into, so for ith particle it will be m multiplied by ri bar perpendicular, okay, cross vi bar, summation of that, where I goes from 1 to n, right? So then you know that v is equal to omega bar cross r bar. Okay, v is equal to omega bar cross r perpendicular bar, right? We had studied this earlier. V is equal to r omega. If you remember, v bar is equal to omega bar cross r perpendicular bar in vector form. Okay, so for a single particle you can say that now I am taking only one component. Which component? The axial component of angular momentum. So it is equal to m multiplied by r perpendicular bar cross v bar, which is omega bar cross r perpendicular bar. And then if you take its magnitude will be, see, you have r perpendicular, that is m multiplied by r perpendicular square multiplied by this omega, and then you get j cap. Okay, right? It is directed along what? J cap. Okay, so this is axial angular momentum of one particle. Then if you add it up for all particles within the body, then you get the angular momentum of total body. Okay, complete body. So for a body, but which body? Symmetric body, I should say. Okay, the total angular momentum is equal to what? Summation of this thing, mi ri square, ri perpendicular square multiplied by omega into j cap. And then what is this term? So we know that this term is equal to the moment of inertia, which we talked about yesterday, right? What is ri perpendicular? It's perpendicular distance of a point from the axis of rotation. So then you get angular momentum is equal to what? I multiplied by omega times j cap, you can say. And what is omega times j cap? So what is direction of omega? It is axial, we know that. So suppose this body is rotating like this, then we curl our fingers in direction of rotation, stretch our thumb. The stretched thumb gives us the direction of omega. Okay, so the direction of omega is along the axis only, and that's why omega times j cap is just omega bar. So you can say L bar is equal to I times omega bar, or L is equal to I times omega. Okay, in scalar form L is equal to I times omega. Is this thing clear to everyone? Okay, good. So L is equal to I times omega, right? So angular momentum is equal to moment of inertia multiplied by omega. We got this. Then now let's talk about the torque and the conservation of angular momentum. So angular momentum of a symmetric body rotating with angular velocity omega can be written as, so angular momentum I am writing specifically of a symmetric body, right? So I am not writing this for any asymmetric body. Okay, but the bodies that we'll see, or the types of objects that we'll see in the problems, they will be all symmetric, almost all symmetric. Okay, so angular momentum of a symmetric body rotating with angular velocity omega can be written as L is equal to I times omega. We saw this. Now suppose we apply an axial torque. Okay, so here also we apply the axial torque because angular momentum is directed along the axis, so we apply an axial torque. How do we apply an axial torque? So suppose you apply some force here. Okay, suppose you are exerting a force. Okay, you are exerting a force on this apple, suppose at any point, let's say at this point. Then what I'm doing is I draw a perpendicular like this. Okay, from this point on the axis. So this is the perpendicular line, or this is the perpendicular distance of the force from axis of rotation. Then the force, if it is perpendicular to this line, then the torque would be axial, because what is torque? Torque is R bar cross F bar. Got it? Yes, no? Yes or no? Okay, torque is axial. So then now axial torque will change the axial angular momentum, right? Our angular momentum is along axis and torque is also along axis. So this axial torque will change the angular momentum, axial angular momentum. So how do we write the rate of change of angular momentum? Rate of change of angular momentum is equal to what? Torque acting on the body. Okay, so then torque can be written as what? T by dt of I times omega. Okay, so we know this from I guess we saw this in last to last lecture. Okay, the torque is equal to rate of change of angular momentum. So if it is true for one particle, it is true for n particles also. Okay, so torque is equal to d by dt of I times omega. Then you take derivative of this, so you have di by dt times omega plus I multiplied by d omega by dt. And if it's a rigid body, then its moment of inertia about a given axis of rotation will not change. Okay, too many concepts, right? Its moment of inertia about a given axis of rotation will not change. What does this mean? It means that our body is rigid, so the configuration of mass of this body about the axis of rotation, it remains as it is. Okay, so mass doesn't change, or mass does not get displaced. Mass does not get displaced means there is no change in shape or size of the body, right? So this di by dt would be equal to 0. The moment of inertia of a rigid body about given axis of rotation does not change. Okay, moment of inertia of a rigid body about any axis of rotation, given axis of rotation, will not change, because the mass of rigid body will not get displaced, okay, with respect to, or suppose there are n number of particles within the rigid body, then particles don't get displaced, okay, with respect to one another, right? And therefore moment of inertia does not change. So for rigid body this term is going to be equal to 0. So what do you have? Torque is just equal to I multiplied by d omega bar by dt. Okay, so what is d omega by dt? It is alpha. So you get another relation, the torque is equal to I times alpha bar. Tau bar is equal to I times alpha bar, or tau is equal to I times alpha in the scalar form, right? Is the thing clear? Is it clear? Yes, no? Okay, very good. Now you can, what you can do is you can go back to this lecture, right? Whatever we are going to whatever we studied till now, because there were too many concepts. Okay, so let me summarize it for you. What we studied is, see, if you have a symmetric body, okay, if you have a symmetric body, and we are going to study symmetric bodies only, so its angular momentum is going to be axial. Okay, there is no radial component of angular momentum. So if you add up the axial components of angular momentum of all particles, then you get total angular momentum of body. Okay, that is first point. Second point is, okay, this is first point. Then now this axial angular momentum will remain constant if you don't exert any axial torque, right? So if you don't exert any axial torque, the angular momentum will remain conserved. But if you exert torque, then what will happen? The axial angular momentum will change if you exert an axial torque. Okay, if you exert torque, let's say you exert a torque, right? And then this angular momentum, we saw that it can be written as I times omega. Okay, it can be written as I times omega. So put angular momentum, torque is equal to dl by dt, put angular momentum is I times omega, then you take derivative of that. So di by dt times omega, you make use of the product rule of derivatives. So di by dt times omega plus I multiplied by d omega by dt. Okay, this is what you get. And for a rigid body, this di by dt is equal to 0, because moment of inertia of rigid body for a given axis of rotation remains constant. It does not change with respect to time, and that's why di by dt is equal to 0. And therefore you have tau is equal to what? I multiplied by d omega by dt, that is I times alpha. Okay, so this is short summary. Okay, even if you remember this much, that's fine. All right, so this is clear, right? Okay, good. So now see, there is a basic one-to-one correspondence, okay, in the language of maths, in quantities in linear motion and quantities in rotational motion. So if you know formulae in linear motion, you know the formulae in rotational motion. How? See, the mass is similar to the moment of inertia. Mass is analogous to moment of inertia, or let's say moment of inertia is analogous to mass. Analogous means similar. Okay, then theta is the angular displacement. It is analogous to linear displacement. Then omega bar, okay, omega is the angular velocity. It is analogous to linear velocity. And alpha is angular acceleration. It is analogous to the linear acceleration. So if you make use of these things, then you can find out all formulae. Okay, so just like in case of linear motion, we have linear momentum. Linear momentum is equal to mass times linear velocity. So just like that, you can write angular momentum. Angular momentum is equal to what? So definition wise, for one particle it is r bar cross p bar, right? R cross p. Okay, it is called as moment of linear momentum. But then for a body, if you want to write it, then so body can have one particle also, right? So just change m by I, right? Analogous quantity of mass is moment of inertia. So just change p by l. Okay, So angular momentum is analogous quantity of linear momentum. Change P to L, M to I, and V to what? Omega. So you get L is equal to I times omega, right? Okay, this is clear. Yes, no. Okay, then let's see next one. Newton's second law. For the case of linear motion, you have F bar is equal to dp bar by dt. Okay, force is equal to rate of change of linear momentum with respect to time. So similarly, you have torque. Torque is equal to rate of change of angular momentum with respect to time. So just change force. Analogous quantity of force in the rotational motion is torque. So torque would be equal to d by dt of an analogous quantity of linear momentum. So that is angular momentum. So just like you have F is equal to dp by dt, this is Newton's second law for linear motion. This is Newton's second law for rotational motion. Torque is equal to what? Rate of change of angular momentum. Okay. And if mass is constant, just like if you have mass constant in linear motion, then force can be written as mass times acceleration. Okay, force is equal to mass times acceleration. Just like that, if I is constant, then we can say the torque is equal to I multiplied by alpha. Okay, torque is equal to I multiplied by alpha. Okay, and then we'll take this analogy one step further. So just like we have work done in case of linear motion is the dot product of force and displacement, just like that work done in case of an angular motion or rotational motion would be equal to take analogous quantity of force, which is torque, and take analogous quantity of displacement, which is angular displacement. So it is dot product of torque and d theta. Okay, and work energy relation. Work energy relation is what? Work done is equal to change in kinetic energy. So now work energy relation remains the same, but here just formula changes. Okay, because we need to write it in terms of rotational motion. So what will be kinetic energy? So just like we have kinetic energy in case of linear motion is half of mv square, here the kinetic energy would be equal to half of I multiplied by omega square. Okay, kinetic energy in the rotational motion is half of I omega square, right? Okay, so work done is equal to final kinetic energy minus initial kinetic energy. So work done is equal to final kinetic energy is half of omega f square, okay, final angular velocity square, minus half of I into omega I square. So this is for rotational motion. And one more thing, that is the power. Power in case of linear motion can be written as F bar dot V bar. In case of rotational motion, you can write power is equal to tau bar dot omega bar. Okay, analogous quantity of force is torque, analogous quantity of velocity is angular velocity, right? So is it clear? Everything, every formula, everyone? Okay, so now this table is very important. Okay, the analogy between linear motion and rotational motion, you need to remember all of these formulae, right? Okay, in exam you should not do this. So this is good for understanding, for the sake of understanding, and if you're doing research etc, it's very good. Okay, so to find the analogy or to finding out the quantities from analogy, but if you are writing NEET exam or JEE exam, so then this formulae should be by heart. Okay, you should remember them. Okay, you can't do this in exam. The torque, okay, it's analogous quantity of force. So then you have force is equal to dp by dt. So just like that, you will have torque is equal to rate of change of angular momentum. Okay, we don't have that much time, right? So we should know this formula. All right, so let us see some problems based upon these things. A solid sphere is rotating freely about its symmetry axis in free space. The radius of sphere is increased, keeping its mass same. Mass is kept same, radius is increased. Which of the following physical quantities would remain constant for the sphere? Angular velocity, moment of inertia, rotational kinetic energy, angular momentum. Tell me. A solid sphere is rotating freely, okay, about its symmetry axis in free space. Symmetry axis means natural axis which is passing through its center. Right? So the solid sphere is rotating like this with angular velocity omega. So option A, angular velocity. Okay. So the radius of sphere is increased. Radius is increased. Okay, this radius is increased, keeping its mass same. Okay, mass is kept same. Which of the following physical quantities would remain constant? This is the question. Okay, so you can think of it this way, that suppose this is a sphere, right, and it's rotating, okay. Now what happens is its radius increases, so because of some reaction, you can say internal reaction, radius increases, means here it's expanding in all directions uniformly, right. So this is because of what? This is because of some internal force, you can say, okay. So now sphere is expanding, okay, radius is increased. Now you are not exerting any external torque on it, okay, no external torque is applied, so the angular momentum would remain constant. And angular momentum will remain constant means angular momentum is equal to what? It is I times omega. Now if sphere is expanding, okay, its radius is increasing, means its I will change, because I is summation of mi ri square, right. I goes from 1 to n. So now mass is going away from the axis of rotation, you can say. So mass is going away everywhere, but here if you see in this direction, mass is going away from the axis of rotation, and that means the moment of inertia will increase. So if moment of inertia increases, what will happen to the angular velocity? It will decrease, right. Yeah, it will decrease. So angular velocity will decrease. Okay, so angular velocity changes, moment of inertia changes, moment of inertia increases, angular velocity decreases. Then what about the rotational kinetic energy? Can we say that it remains constant? So rotational kinetic energy is half of I omega square. I is changing, omega is changing, rotational kinetic energy will not remain constant, right. So rotational kinetic energy also changes, so only one thing remains constant, that is angular momentum. Okay, if you don't exert any external torque on the system, then its angular momentum will remain conserved and these quantities will change. Okay, this thing is clear. Why will they change? Is it clear? Yes, no? Alright, good. So this is the answer. Angular momentum will remain conserved. So now they have asked this question in different ways. Okay, so we need to remember that if there is no external torque acting on a system, then angular momentum will remain conserved. Okay, alright, let's see next one. Two disks of same moment of inertia rotating about their regular axis, passing through center and perpendicular to plane of the disk. There are two disks of same moment of inertia rotating about their regular axis passing through center and perpendicular to plane of disk has angular velocities omega 1 and omega 2. They are brought into contact face to face, coinciding the axis of rotation. Okay, the expression for loss of energy during the process is, okay, who can tell me what should we do here? You have two disks like this. This is first one. Okay, and you have another disk, similar disk, and they are rotating with angular velocities omega 1 and omega 2, right? And now they are brought in contact. Okay, one is kept over another. So then what will happen? How much would be the loss in kinetic energy? This is the question. Okay, so once again, what we can say here is you are not exerting any external torque. Okay, these two disks are kept one over the another. So there is no external torque. No external torque means their angular momentum will remain conserved. Okay, so angular momentum, total angular momentum is constant, right? So therefore I can say initial angular momentum is equal to final angular momentum. So I1 omega 1 plus I2 omega 2 is equal to, now when they are kept in contact with each other, what will happen? Eventually their velocity, angular velocity will become equal, right? Okay, their angular velocity when they are kept in contact with each other, let's say after some time, their angular velocities will become equal. So I can say I1 plus I2, it is I1 plus I2 multiplied by omega. Okay, let's say omega final, omega f, and therefore what will be the omega final? Omega final is equal to I1 omega 1 plus I2 omega 2 divided by I1 plus I2, right, divided by I1 plus I2. Okay, so this is final angular velocity, and then I want to find out the change in kinetic energy. So what would be change in kinetic energy? The change in kinetic energy, delta Ke, is initial kinetic energy. Okay, so initial kinetic energy, Ke initial, let's say Ke I minus Ke final. Okay, that is equal to half of I1 omega 1 square plus half of I2 omega 2 square. Okay, now in this example I1 is equal to I2, but I want to find out general relation. That's why I am solving with different I1 and I2, right? In this example what they have given is the two disks have same moment of inertia. Okay, but I want to find out general relation, and that's why I am solving with different I1 and I2. Okay, at the end we'll put I1 is equal to I2, right? Okay, so kinetic energy, initial kinetic energy is this one, half of I1 omega 1 square plus half of I2 omega 2 square minus final kinetic energy is half of, now how much would be their moment of inertia? So it is sum of I1 plus I2. Okay, so it is half of I1 plus I2 multiplied by omega f square. Okay, and you put omega f is equal to what? So that is equal to this thing. This is initial kinetic energy of the two disks minus half of, you have I1 plus I2, right, multiplied by omega f is I1 omega 1 I1 omega 1 plus I2 omega 2 divided by I1 plus I2, and you have square of that. Okay, you have square of that. Then what happens is this square gets cancelled with this I1 plus I2, and then you can simplify it. Okay, so you have half of I1 omega 1 square plus half of I2 omega 2 square, okay, minus, it will be I1 omega 1 square, okay, minus half of I1 omega 1 plus I2 omega 2, then you have square of that divided by I1 plus I2, right? So now if you solve all of this, I mean if you simplify this thing, then at the end what you will get is, you will get half of I1 I2 divided by I1 plus I2 multiplied by omega 1 minus omega 2 square. Okay, this is delta Ke, right? Is this thing clear? So I am not solving and simplifying, I am just stating that if you do that, all of that, right, all simplification, at the end you will get this answer. Okay, so let me add this in the topic. Okay, and so if if two bodies rotating two bodies rotating with angular velocities with angular velocities omega 1 and omega 2 are brought in contact, then loss in kinetic energy is, so we want to find out loss in Ke when two bodies with angular velocities omega 1 and omega 2 are brought in contact. They are rotating with angular velocities what, omega 1 and omega 2. So I1 is mi of first body, moment of inertia of first body. I2 is moment of inertia of the second body, right? This is just for an example. Okay, so this can be discs, this can be rings, etc. Okay, so now does this formula remind you of something? Half of I1 I2 divided by I1 plus I2 multiplied by omega 1 minus omega 2 square. Yes. Okay, see, if you remember, in case of inelastic collision where two bodies stick together, right, in inelastic collision two bodies stick together, in that case loss in kinetic energy is equal to, remember, in case of inelastic collision. Okay, compare with this thing, inelastic collision, okay, so there you have delta Ke is equal to half of m1 m2 divided by m1 plus m2 multiplied by u1 minus u2 square. Right? Do you remember this? So then you can say that just change masses of the bodies to moment of inertia, because this is what rotational motion. Change velocities to angular velocities and you will get the formula for loss in kinetic energy. Is this thing clear? You can compare the two formulae and they are similar. Right? In fact, all this calculation you can find it. We have seen this in case of inelastic collision, loss in kinetic energy, okay, in case of inelastic collision. So if you just change mass over there to the moment of inertia and angular velocity, linear velocities to angular velocities, okay, you can just follow those steps and you will get this final answer. Right? So is this thing clear, everyone? Okay, is there a doubt in this? No doubt, right? Okay, good. So then let's come to the problem, and then you have, this is the change in kinetic energy. Okay, so now I have included this in the topic, so I will just erase this thing. Okay, so delta k is just half of I1 I2 divided by I1 plus I2 multiplied by omega 1 minus omega 2 square. So that is equal to half of, so if moment of inertia is equal, so this will become I square divided by I1 plus I2 is 2I. Okay, moment of inertia is equal, multiplied by omega 1 minus omega 2 square. So this square will get cancelled with the I. 2 times 2 becomes 4. So you have I by 4. So it is I by 4 multiplied by omega 1 minus omega 2 square. So it is option A. Right, it is option A. Okay. This is clear? Yes, no? Okay, good. Alright, so this is simple, right? But if you go and solve it in exam or maybe in some books, if you find this is some 2017 question, no? So if you find the solution, etc., so it's lengthy, right? So you'll feel the question is not worthy of solving. Okay, but it is totally worth. You just need to use this formula, right? Nothing else. Okay, let's move on to the next question. Two rotating bodies A and B of masses m and 2m with moments of inertia I1 and IA and IB. IB is greater than IA. Two rotating bodies of mass m and 2m, masses are different, with moment of inertia IA and IB. IB is greater than IA. Okay, have equal kinetic energy of rotation. If LA and LB be their angular momenta respectively, okay, then which one is greater? This is the question. So now bodies have equal kinetic energies of rotation, so that means you can write this formula, half of I omega square. Okay, this is equal, but instead of that what we are going to do is, so we remember for kinetic energy we have two formulae. One is half of mv square in terms of velocity, mass and velocity. Second one is in terms of momentum, so it is p square by 2m, right? P square upon 2m. So just like that, just replace p with L, so you get formula for kinetic energy here. It is L square divided by 2 times I. Right, L square by 2I. This is kinetic energy. Okay, yes, no? and kinetic energy is equal. Okay, so now you don't need to think about mass because IB is greater than IA is given directly. IB is greater than IA, so don't need to think about mass because radius etc. is not given. Okay, so this is extra information not needed. IB is greater than IA. Okay, so then what will be relation between the angular momentum? So you can say that since energy is equal, EB is equal to, or EA is equal to EB, you can say LB square divided by IB is equal to LA square divided by IA, right? And then IB is greater than IA. So IB is greater than IA means LB square must be greater than LA square. Okay, since denominator of this one is greater than denominator of this one, but the ratio is equal, that means numerator of this one must be greater than numerator of this one. You can do it this way, or you can say that LB divided by LA square is equal to IB divided by IA, right? IB is greater than IA means the numerator is greater, denominator is less. So this is greater than 1. Okay, this is greater than 1, not equal to, greater than 1. This is greater than 1. So if this thing is greater than 1, that means LB by LA square is greater than 1. And if LB by LA square is greater than 1, means LB by LA is greater than 1 too. And therefore LB, oh, what happened? LB by, no, that's correct, right? So LB is greater than, okay, LA. This should be the answer, right? So it's option C. Right? This thing is clear? Yes, no? Okay. So let me just check once. LB square by IB is equal to LA square by IA. I will move this thing on this side, this thing on this side. Yeah, so this thing LB by LA square is equal to IB by IA. That's correct. And IB is greater than IA means that is greater than 1. So LB by LA square is greater than 1 and therefore LB is greater than LA. No problem. Right? Okay, this is clear, everyone? Right, Nikita, is it clear? Okay, good. Let us see next one. Two disks are rotating about their axis normal to the disk and passing through the center of the disk. Disk D1 has 2 kg mass and 0.2 meters radius. Okay, so M1 is 2 kg and radius is 0.2 meters and initial angular velocity of 50 radians per second. So omega 1 is 50 radians per second, and disk 2 has 4 kg mass, 0.1 meter radius and angular velocity of 200 radians per second. So this 2 has mass m2 is equal to 4 kg, 4 kg. Then radius r2 is equal to 0.1 meter and angular velocity omega 2 is 200 radians per second. The two disks are brought in contact. So this kind of problem is repeated. We saw similar problem earlier too, right? Two disks are brought in contact face to face with their axis of rotation coincident. The final angular velocity in radians per second of the system is. This is simple, right? So again we'll say that there is no external torque, they are just kept, the two discs are kept over one another, okay? So no external torque, so angular momentum is conserved. Tau is equal to 0 means L is conserved, and therefore you can say I1 omega 1, okay, initial angular momentum is I1 omega 1 plus I2 omega 2 is equal to final angular momentum. So when they are brought in contact, what will happen? So the moment of inertia will be just sum of the moment of inertia of two bodies. So I1 plus I2 multiplied by angular angular velocity is omega f, okay? So omega f is equal to I1 omega 1 plus I2 omega 2 divided by I1 plus I2. Okay, so henceforth you can directly write down this formula, right? Angular velocity, final angular velocity is just I1 omega 1 plus I2 omega 2 divided by I1 plus I2. Okay, then we just need to put values here because this is a disk. So what will be moment of inertia? What is moment of inertia of a disk? It is mr square divided by mr square upon 2, moment of inertia of a disk, right? So then we just need to put values. So let's put values in this formula. Okay, so this thing is just 12 divided by 12 times 100. This is 100, right? So answer is 100 radians per second. Okay, answer is 100 radians per second. So that's the answer. So it is option B. Okay, it's option B, 100 radians per second. Okay, so if we just put the values of these things, we get 100 radians per second. Okay, let's move on to the next one. So a circular platform is mounted on a frictionless vertical axle. Its radius r is equal to 2 meters and its moment of inertia about the axle is 200 kg meter square. It is initially at rest. A 50 kg man stands on the edge of the platform and begins to walk along the edge at the speed of 1 meters per second relative to the ground. Then time taken by the man to complete one revolution is. Okay, a circular platform is mounted on a frictionless vertical axle. This is given. Okay, so you have this vertical axle, right, and there is a circular platform. There is a circular platform like this, and it is mounted on this axle, right? So then what do you have? Its radius r is equal to 2 meters and its moment of inertia is 200 kg meter square. Okay, so radius is given, r is equal to 2 meters and moment of inertia of this platform I is equal to 200 kg meter square is given. Okay, then it is initially at rest. The platform is initially at rest. This is also given, right? So then a 50 kg man stands on the edge of the platform. So there is a man who stands on the edge of this platform, okay, and he begins to walk along the edge. So this man begins to walk along the edge. So suppose he walks in forward direction, then what will happen? So he pushes the platform back, right? He pushes the platform in backwards direction. Okay, so if he is walking like this, so suppose this is a man, he is walking on the ground. Okay, so we know that in order to walk on the ground, he has to push the ground backwards, then ground will exert force in forward direction and he will be able to walk. So just like that, here he is walking along the edge of the platform. So at this point, you can say if he is walking like this, then he exerts a force on platform in backwards direction, that is in tangential direction. Okay, like this. So then, so weight of the man, so let's say mass of the man, how do I write this? So let's say m is the mass of man only. Okay, so that is equal to 50 kg, and he begins to walk with a speed, so speed of man is equal to 1 meters per second. This is given. Then time taken by the man to complete one revolution is, what would be the time taken by the man to complete one revolution? This is the question. Okay, so somebody might say that he is walking with the speed of 1 meters per second, and the distance that has to be covered is 2 pi r. What is r? R is 2 meters, right? Radius is 2 meters. So 2 pi multiplied by 2 divided by 1. Okay, so that is 4 pi. Is that the answer? It's not the answer. Okay, and fortunately 4 pi is not given there, so we can correct ourselves. Okay, even if we do this mistake, right? But if 4 pi was given, then you can, then mistake is possible. Anyways, but this is not the answer. This is not the correct way. What's happening? Man is walking along the edge of the disk, and therefore what will happen? He is exerting force in backwards direction. But now if you consider the system of the disk and man, it is one system, so total angular momentum should remain conserved, right? Total angular momentum should remain conserved. There is no external body which is exerting any force. It's the man walking on the disk. Okay, total angular momentum should remain conserved, right? Okay, therefore I can say initial angular momentum, initially both were at rest, so L initial is equal to 0, and therefore it should be equal to, L is conserved, L is constant because no external torque. Okay, why is it constant? Torque is 0, so L is constant. Okay, so therefore you have L initial is equal to 0, and what is L final? So the angular momentum of man plus angular momentum of platform must be equal to 0. So now what is angular momentum of man? Tell me. It is moment of linear momentum, right? So it is r multiplied by mv. Okay, r multiplied by mv. Actually it is cross product, r cross mv, but velocity is tangential, right? He is walking like this. So if you take r cross v, then angle between them is 90 degree, and you have r cross mv. Okay, r cross mv, so it is mvr sine of 90, right? Sine 90 is 1, and therefore you can directly take r multiplied by mv. This thing is clear, because angle between the radius and his velocity is 90 degrees. Okay, so rmv plus angular momentum of the platform. How can you write angular momentum of platform? It is I times omega. Okay, it is I times omega, so that is equal to 0. Okay, so then you can move this r times mv on other side. Okay, so you get I omega is equal to minus of mvr, and therefore omega, the angular velocity of platform, is equal to mvr. It was small m, no? Okay, small m, mvr divided by I, and then we can put the values. That is minus of mass of man is 50 kg, his speed is 1, radius is 2, and divided by, in denominator you have moment of inertia of the platform. Okay, moment of inertia of the platform is 200, right? So in numerator it's 100 divided by 200 is 0.5, so omega is equal to minus 0.5 radians per second. So what does this minus mean? It means that if man is moving in forward direction, or suppose man is moving in clockwise sense, then the platform will move in anti-clockwise sense, right? This negative sign means the man is moving in clockwise sense, then what will happen to the platform? Platform will rotate in the anti-clockwise sense, okay, right? Then now see, man is moving in forward direction, okay, and in order to complete one revolution he has to come back to the same point. But now platform, if platform was steady, then you can say the distance to be covered is 2 pi r and his velocity is v. Now you need to take his relative velocity with respect to platform. He is moving, okay, and platform is also moving, right? So find out velocity of edge of the platform, okay, find out velocity of edge of the platform. What is velocity of the edge of the platform? So it will be equal to velocity of platform, let's say it is equal to r times omega. What is r? R is 2, so 2 times 0.5, okay, but it's negative, so it's minus 2 times 0.5 means minus 1 meters per second, and therefore now time taken for one revolution, okay, time for one revolution would be equal to what? The distance covered, okay, let's say t is equal to distance covered 2 pi r divided by relative velocity of man with respect to platform. So this is a good question, relative velocity of man with respect to platform. So you have 2 pi r, so 2 pi r, in options pi is kept as it is, no, so 2 pi multiplied by, okay, r is capital, so the value of r is 2 meters, right, divided by velocity of man is 1, velocity of platform is minus 1, platform is moving in opposite direction, okay, so that is 1 minus minus 1 means 2, so 2 and 2 will get cancelled, so it is 2 pi. So t is equal to 2 pi seconds, right? So that is the answer, it's option C. So this one is clear, everyone? Right, everyone? Porna?
Yes, sir.
Okay, good. All right, good. Let's see next one. Okay, a circular disk of moment of inertia it is rotating in a horizontal plane. Okay, a circular disk with some moment of inertia it is rotating in horizontal plane. About its symmetry axis means, natural axis. Okay, natural axis means, always remember, perpendicular to plane passing through the center. Okay, another disk of moment of inertia IB is dropped coaxially onto the rotating disk. So another disk is dropped coaxially, kept on the first disk. Initially the second disk has zero angular speed. Eventually both the disks rotate with constant angular speed omega f. The energy lost by the initially rotating disk to friction is, oh, option D. Very good, because we have direct formula now, right? So see, this kind of question is repeated many times, okay, many times. I guess we are seeing it fourth time. This is 1, this one was 2, okay, where I did some calculation mistake. This one was 2, right? This is 3, no, third time, okay. All right, so answer is, what is the answer? Delta KE is equal to half of I1 I2, okay, I1 I2 divided by I1 plus I2 multiplied by omega 1 minus omega 2 square. So they are calling first the moment of inertia of first disk as IT, moment of inertia of second disk as IB. So it will be IB times IT divided by IB plus IT multiplied by angular speed of first one is omega 1, angular speed of second one is 0, so omega 2 is 0, okay, and that's why it will be the answer. Okay, ITIB divided by IT plus IB, IT plus IB multiplied by omega I square. Good. So this is the answer, right? Very good, Indusha. So this is simple. There is nothing in this or this kind of question now, right? Okay, we just need to remember the formula. Okay, let's see next one. A thin circular ring of mass m and radius r is rotating about its axis with constant angular velocity omega. Okay, ring is rotating about its axis with angular velocity omega. Two objects each of mass m are attached gently to the opposite ends of diameter of ring. You have a ring and two masses are applied gently to the ring. We have this ring and two masses are attached, one on this side, one on this side. Okay, so mass of the ring is capital M, these masses are small m, and the ring now rotates with angular velocity given by, again the same concept, right? So since you are attaching the masses like this, okay, there is no force in plane of rotation of in the plane of rotation of the ring, and therefore its angular momentum should remain conserved, because since there is no force in the plane of rotation, the torque will remain the axial torque will remain 0. Sorry, what did I say? Torque will remain. Torque will be equal to 0, so angular momentum will remain conserved, right? So torque is equal to 0, therefore L remains conserved. Okay, so initial angular momentum. What is initial angular momentum? Moment of inertia of ring, you can say, multiplied by omega is the initial angular momentum. Okay, and then this is initial angular momentum. It should be equal to final angular momentum. So that is equal to moment of inertia of ring plus these two masses. So what is moment of inertia of masses? 2 times of mr square multiplied by final velocity is omega f. Okay, so therefore omega f is equal to moment of inertia of ring. What is moment of inertia of ring? It is mr square, right? Mr square, okay, times omega divided by mr square plus 2mr square, right? We are just taking this thing on the other side, so times omega, so r square will get cancelled out. What's the answer? It is just m divided by m plus 2m. This is the times omega. This is the answer. Okay, so there is omega in option, m divided by m plus 2m times omega. Oh, omega is there, no? I thought they have just written m upon m plus 2m, right? So it is option D. This is very simple, right? Okay, this one is very simple. Let's see next one. I guess this is similar. A round disk of moment of inertia I2 about its axis perpendicular to plane and passing through its center is placed over another disk. See, repeated one, another disk, okay, of moment of inertia I1 rotating with angular velocity omega. The final angular velocity of the combination of disks is, what is the final angular velocity? Tell me, which one is rotating? I2. This one is rotating. Moment of inertia, a round disk of moment of inertia I2 about its perpendicular axis passing through the center is placed over another disk having moment of inertia I1. No, I1 is rotating, okay, with the angular velocity omega. Okay, so once again you can say the initial angular momentum is equal to final angular momentum. So L initial or Li, let's say, is equal to Lf. Okay, so this thing is I1 plus I2 times omega f, and this one is I1 times omega. So the answer is omega f is equal to I1 divided by I1 plus I2 times omega. Okay, so it is option C. You can directly use the formula, what? I1 omega 1 plus I2 omega 2 divided by I1 plus I2. You can directly use this formula. Okay, omega 2 is 0, the second disk is not rotating, so this thing is 0. So you have I1 times omega 1, omega 1 is given to be equal to omega. So I1 omega divided by I1 plus I2. This is the answer, right? So this one is simple, repeated many times. Okay, there is nothing in this question. Let's see next one. Okay, so a thin circular ring of mass m and radius r is rotating about its axis with constant angular velocity omega. See, this one is also repeated. 4 objects, each of mass m, are kept gently to the opposite ends of 2 perpendicular diameters of the ring. The angular velocity of the ring will be, tell me quickly. It is just like the previous one. It is option B, right? We just solved a problem like this, no? So here 2 masses were connected, there 4 masses are connected. What's the difference? No difference, right? So in place of 2m, there will be 4m. Is this thing clear? Okay, good. So this is repeated one. Okay, so as I can see, at least 3 times in these questions. Let's see next one. A disk is rotating with angular speed omega. If a child sits on it, what is conserved? Repeated. Tell me. What is conserved? Linear momentum, kinetic energy, potential energy? Yes, it's angular momentum. Okay, angular momentum is conserved. Right, let's see next one. The instantaneous angular position of a point on rotating wheel is given by this thing. The torque on the wheel becomes 0 at. This is the question. So how do we solve this one? So torque becomes 0. This is given. Tau is equal to 0. Means I alpha is equal to 0. Right? But moment of inertia cannot be equal to 0. Means alpha is 0. And what is alpha? It is angular acceleration. So just find out angular acceleration, equate it to 0 and you will get the time. So let's do that. So you have d theta by dt is equal to d by dt. This is omega, right? D theta by dt is omega. Omega equals to d theta by dt, and that's d by dt of 2t cube minus 6t square. So omega is equal to, it is 2 times 3t square minus 6 times 2t. Okay, so 6t square minus 12t, this is omega, but we want alpha, which is d omega by dt, and that is equal to d by dt of 6t square minus 12t. Okay, so take its derivative. The derivative of t square is 2t. We have 6 multiplied by 2t minus 12, and this is equal to 0. So 6 times 2t means 12t. 12t minus 12 is equal to 0. Okay, alpha is 0 means this thing is 0. So 12t is equal to 12 means t is equal to 1. T is equal to 1 second. So this is the answer, option A. Okay, this is clear, very simple, right? Yes, no? Okay, it's very simple, right? Let's see next one. A wheel has angular acceleration of this much, 3 radians per second square, and initial angular speed of 2 radians per second. In the time 2 seconds, it has rotated through an angle of, okay, tell me quickly. A wheel has angular acceleration is given, angular speed is given, and time is given, and it rotates with certain angle. So alpha is given, okay, initial angular velocity is given, alpha is equal to 3 radians per second squared, omega naught is given 2 radians per second, and time is given, time is 2 seconds. And question is, it rotates through some angle. So this is direct question, theta is equal to omega naught t plus half of alpha times t square, right? We just need to make use of the kinematic equation for rotational motion. Okay, so that is 2 times of t, t is 2 plus half of alpha is 3 times 2 square means 4, 4 by 2 is 2, 2 times 3 is 6, so 4 plus 6 means 10, so 10 is the answer, 10 radians, option A, right? Very simple. Okay, good. Let's see next one. A wheel having moment of inertia of 2 kg meter square about the vertical axis rotates at the rate of 60 rpm. It rotates at the rate of 60 rpm about the axis. Torque which can stop the wheel's rotation in 1 minute would be. Okay, wheel has some moment of inertia. It's given, I is given, right? Then omega naught 60 rpm, no? So original frequency you can say, let's say n naught is equal to 60 rpm means 60 divided by 60 revolutions per second. Okay, so 1 rps, this is given, and nt is equal to 0. Okay, final frequency is equal to 0. It stops means final frequency would be equal to 0. So you want to find out the torque. This is very simple, and in 1 minute, they say in 1 minute time is equal to 60 seconds, right? Time is equal to 60 seconds. So we know tau is equal to I times alpha, just put the values, nothing else, right? So I is 2 multiplied by alpha is omega f minus omega naught divided by time, so that is 2 multiplied by final angular velocity is 0, and omega naught is just equal to what, 2 pi times f naught, or 2 pi times we are taking n, right, n naught divided by time is 60. So this is 2 by 30 by 15, okay, pi n naught by 15 minus pi times n naught is 1 divided by 15. Okay, so answer is minus pi by 15 Newton meters. Okay, so it is option C. They have just asked about the magnitude. Negative sign means it is stopping, right? Angular velocity is decreasing. Okay, if there is positive sign, angular velocity is increasing, right? This is the answer. Okay, clear? Yes, no? Okay, this one was, again, this is simple. See, we are seeing all types of questions. A rope is wound around a hollow cylinder. A rope is wound around a hollow cylinder of mass 3 kg and radius 40 centimeters. What is the angular acceleration of the cylinder if the rope is pulled with a force of 30 Newton? There is a cylinder like this, and a rope is wound. Okay, a rope is wound to that cylinder. Let's say like this. Okay, and if you pull this rope, let's say in this direction, you pull the rope with some force. Okay, so then what will be the angular acceleration? This is the question. Tell me. So if you are pulling the rope, means you are exerting some tangential torque. Sorry, what did I say? This is tangential force, not tangential torque. So suppose if you are pulling the rope, then there will be some torque acting on it, right? So force is tangential. Okay, so torque will be equal to what? R cross F. Torque will be equal to R cross F. So R F sine theta, you can say torque is equal to R F sine theta, and force is tangential, that's why theta is equal to 90 degrees. So it is just R times F, and you can say because of this torque, what will happen? The cylinder will rotate, okay, with some acceleration, and the torque for the cylinder can be written as, because we are exerting this torque on the cylinder, so in terms of the angular acceleration, we can write this torque as I into alpha. So I times alpha is equal to R times F, okay, because theta is 90, sine 90 is 1, okay, so you have R times F, and you want angular acceleration only, so it is Rf divided by I. Very simple. And its moment of inertia is not given, instead the mass and radius is given. So we know what is moment of inertia of a cylinder. It is mr square by 2. You have R times F divided by mr square upon 2. One R will get cancelled with this R. So 2F divided by mr. Okay, therefore alpha is 2 times F divided by mr. Just put the values. 2 times force is 30 Newton divided by mass is 3 kg and radius is 40 centimeter. So 40 multiplied by 10 raised to minus 2, right? So then 30 divided by 3 is 10. Okay, then you have what? 40 divided by this 2 is 20. Take 10 raised to minus 2 in numerator, so it is 10 raised to plus 2. 10 raised to 2 times there was 10 here, so that is 1000 divided by 20. Okay, check my calculation. 30 divided by see, this R and R gets cancelled, so you have mr. Take 2 in numerator, so you have 2 times 30 divided by 2 multiplied by 40 into 10 raised to minus 2. Okay, so 30 by 3 is 10, so this thing will be 20 in numerator. 20 by 40 means 0.5. 0.5 into 10 raised to minus 2, sorry, 10 raised to plus 2 it will be. Okay, so it has to be 50, I guess. Oh, it's a hollow cylinder. Nice. It is not solid cylinder, it's hollow cylinder. So hollow cylinder, no? So for hollow cylinder, moment of inertia is mr square. I thought it's a cylinder, I took mr square by 2. Okay, it's a hollow cylinder. So note 2 here. Okay, then it will be just just what 30 by 3 is 10. Okay, so 10 by 40 means 0.25. 0.25 times 10 raised to minus 2 in numerator, 10 raised to plus 2. So it will be 25, right? 25 radians per second square. That is the answer. So it is option B. Okay, this thing is clear, everyone? Okay, a simple question, but then we need to read it carefully, right? So I thought, okay, it's a cylinder, mr square by 2, but it is hollow cylinder. All right. So then rolling motion and all we'll see tomorrow. We'll stop here.